Okay, so previously we've seen how to show that an n-dimensional hypercube graph is bipartite, and now what we're going to do is have a look at this for an infinite dimensional hypercube graph. So just a really quick recap of the n-dimensional case. So your set of vertices, it's really convenient if you write these as x1 up to xn, the n-dimensional hypercube graph, such that each of your coordinate entries are either equal to 0 or 1. And then this is really helpful because then there is an edge between two vertices. This is if and only if exactly one of their coordinate entries are different. And then using this fact, this can lead us to a nice partition to show that the n-dimensional, finite dimensional hypercube graph is bipartite. And a bipartite graph, this basically means you can partition to two disjoint sets, partition all of the vertices so that there are no edges connecting a pair of vertices in A, there's no edges connecting a pair of vertices in B, but you are allowed to have edges going from A to B. So we came up with a really nice way of partitioning this. So it's a very elegant proof. You partition into a set of all vertices such that the sum of all the values is even as your A, and then B is the same set, basically, but where the sum is odd. And it turns out that this gives you a really nice partition here. So if you were to try this for the infinite dimensional case, so for an infinite dimensional hypercube graph, it's possible that this sum could be infinite. So for example, you might have a vertex like this, where it just goes 0, 1, 0, 1. The sum of all these values would be infinity, so that's not clear whether that's odd or even. So unfortunately, we'll need a different argument to show that the infinite dimensional hypercube graph is bipartite. So the first thing that we're going to do towards proving this for the infinite dimensional case is we're actually going to define an equivalence relation, which is going to be really useful on all the vertices. You say that if you've got two vertices, x1, x2, and so on, say that this is related to y1, y2, ... if all but finitely many of their coordinates are the same. So they're not allowed to have an infinite number of different coordinates. So just a couple of examples, if you have 0, 1, 1, 1, where the ones repeat forever from there, this would be related to 1, 1, 1, 1, where you've got infinitely many ones, because there's only one difference there, the 0 and the 1 are different. But for example, if you had 0, 1, 0, 1, 0, 1, where it always alternates between 0 and 1, this wouldn't be related to 1, 1, 1, 1, because even though you've got infinitely many that are the same, or these ones match up, you've also got infinitely many which are different, and you're only allowed to have finitely many that are the same, or 0. And it's not too difficult to show that this is a proper equivalence relation, that it's reflexive, it's symmetric, it's transitive. We're going to move on now and we'll apply this equivalence relation because this will help split up all of our vertices into equivalence classes, which we can then use to form our partition to show that the graph is bipartite. So we've split up our vertices using this equivalence relation into lots of equivalence classes where within each equivalence class, each vertex, you can go from one to the other by changing finitely many coordinates. But if you wanted to go from one vertex in one class to one vertex in another class, you would need to change infinitely many coordinates. So we're going to use this partition now into the equivalence classes to define our partition to show that this infinite dimensional hypercube graph is bipartite. So the first thing we're going to do is we're actually going to use the axiom of choice here, and all we're going to do is we're going to choose a vertex from each equivalence class. So here, basically, we're using the axiom of choice because there isn't necessarily a way of using a fixed rule to choose a vertex. You can't choose the one that has the most ones in it. So there might be infinitely many, and you could have as many as you like. You can't choose the one that has the most zeros or choose one that follows a certain pattern. So this is where we're relying on the axiom of choice to be able to just make this choice to get us started. We've chosen a vertex from each equivalence class. And then what we're going to do is we're going to put all of these vertices into a set A. So we're going to partition into a set A and a set B. So just at this point, we've got a set A which is full of vertices. None of them are in the same equivalence class. There's actually, to go from one vertex to another, you would need to travel along infinitely many edges. There are infinitely many coordinates different. So there's certainly no edge connecting any two vertices in A so far. So this is definitely, we're on the right track to get a nice partition to show that this is bipartite. And then what we're going to do next is we're going to define A as the set of all vertices with an even number of coordinates different from their chosen vertex in their equivalence class. So I call this the chosen vertex, the one that we've already chosen from each equivalence class. So this is our set A, and then B, might be able to guess, is going to be the set of all vertices with an odd number of different coordinates. From their chosen vertex. Okay, so we've got odd and even. This certainly covers all of them because they're all in an equivalence class and there's only a finite number of steps to go from one to another. They'll have finitely many coordinates different. So we've defined a nice partition here, and now the next thing we're going to do is actually prove that there are no edges between vertices in A and there are no edges between vertices in B. So let's consider A first. We have two vertices, we'll say V1 and V2. Let's have V1 and V2 in A. So first of all, you consider if these are in different equivalence classes, then clearly there can't be an edge between them because there's actually infinitely many coordinates different if they're in different equivalence classes. But in order to have an edge, there's only exactly one coordinate different between them. So for sure, if they're in different equivalence classes, there can't be an edge joining them. So now, if they are in the same equivalence class, then we'll assume for a contradiction that they share an edge. So we'll assume that they're both in A, they're in the same equivalence class, and we'll assume that they share an edge, which means that they have exactly one coordinate entry, which is different. So if I write out V1 as, I'll write the coordinates as x1, x2, and then we'll say that xk is the one that's different between them. So V2, they're basically all the same coordinate entries other than xk dash here is different from xk. So now we know that they're both in A, so there has to be an even number of their coordinate entries which are different. So V1 has, we'll say it's 2n, where n could even be 0 if V1 is the chosen vertex. So there are 2n coordinates different from the chosen vertex. So what does this tell us? Well, let's consider a few cases. So if xk is the same as in the chosen vertex, and what does that tell us? Well, that means that xk dash is different, but we know that V1 has 2n coordinates which are different. It can't be one of these because we've assumed that it's the same. So this tells you that V2, with this one different as well, So v2 would actually have to have 2n plus 1 coordinates different. So that's a contradiction because this is an odd number and we've assumed they're both in A. Okay, so that's no good. So what if xk was different from the chosen vertex? So if xk is different, then that means that xk dash would actually have to be the same. So in v1, you've got 2n coordinates which are different from the chosen vertex, and this is one of them. So you've got another 2n minus 1 other than this one, but then here, because this one has to be the same, you only end up with 2n minus 1, which are different from the chosen vertex. And of course this is a contradiction because v2 has to have an even number of coordinate entries which are different from the chosen vertex. So that tells us then there are no edges between vertices in the set A. And then it's a very similar argument for B, where you do the same. If they're in different equivalence classes, surely there's no edge between them. And if they are in the same equivalence class, say if one of them has 2n plus 1, then that guarantees that the other one would have to have either 2n plus 1, that guarantees your other one has to have 2n or 2n plus 2 vertices, and that's your contradiction. So then we've actually managed to conclude then, we've proven that there's no edges between vertices in A and there's no edges between vertices in B, so therefore the infinite dimensional hypercube graph is indeed bipartite. And just to sort of finish off here, I'm going to try and draw a picture of what this partition looks like, which is a bit difficult because we've now got infinitely many equivalence classes all related to each other. So imagine A is my set A of all the ones with an even number of coordinates different, and we'll say B is all the ones with an odd number of coordinates different. Basically how I'm going to draw this out is, if you imagine you've got your chosen vertex here for each equivalence class, we'll say this is the chosen one for the first equivalence class, then this is connected to lots of different ones in your first equivalence class, and then your second equivalence class we can draw out like this. And these carry on forever, so these are all your ones with 0, these are all your ones with 1 different, these are all your ones with 2 coordinates different, and so on. And then you've actually got infinitely many equivalence classes as well. So the picture would look kind of like this. You start off with your chosen vertex in A. This is connected to all the ones that are just 1 coordinate different, and these are connected to all the ones that have 2 coordinates different. But then this does give you a nice partition.